So good morning, let us start. So you have the nth order linear differential expression here, and the corresponding non-homogeneous equation is given by Lx plus Bt equal to 0. We assume all the Pi's are sufficiently smooth in the sense that they can be differentiated as many times as you want. Because you can restrict that. There is no reason why you should consider C infinity functions alone, but just sufficiently many times differentiable. For instance, you can consider them as Cn minus 1 or Cn. Yeah, then B is assumed to be continuous. The homogeneous equation is Lx equal to 0. The equivalent system that you have is dx by dt equal to Atx, where At is given by the n by n matrix, which is constructed using the coefficient functions. Now, the initial value problem is xt naught, that is x evaluated at some point t naught. Its all the derivatives up to the order n minus 1 is evaluated at, this is t naught, at t naught equal to, it's at the same point t naught on the interval t1 to t2. That's what is called the initial value problem. The corresponding system is that dx by dt equal to ax, where x t naught is x naught, where x naught is taken as these vectors. Now, what we have already seen is that the solution space of the homogeneous equation, namely Lx equal to 0, is a vector space and its dimension is n. This is quite easy to prove. What you prove is the following. You look at the corresponding system. Okay, so whatever is happening on the system is happening on this particular homogeneous equation also. So the solution space is obtained with the, if you have a vector capital X, the solution of the homogeneous system, then the first component is the solution of the homogeneous nth order linear equation. Okay, that's the connection between the two. Now you see, all that you prove is that this a set of solutions x1, x2, etc., xm or I can use the phi 1 t, phi m t are linearly dependent if and only if the corresponding solutions x1 of the equivalent system are linearly dependent. And observing that the first component of x1t is phi 1, etc., first component of xnt is phi n. So that's the relation between the phi i's and xi's. Okay. So having got this, now what next? So a consequence of this is that, I mean, using this result, one can prove that the solution space of equal to 0 has dimension So this is the scenario that you have, and these are all very simple to prove. Okay. Now we look at the functions phi 1, phi 2, etc. phi n. Now we can see what is x1, x2, etc. xn. x1 is actually phi 1 derivative, phi 1 derivative n minus 1. This is your x1, and phi 2 this is what you have. So this corresponds to x1, this corresponds to x2, this corresponds to x. So what does it say? It says that x1, x2, etc. xn are linearly independent provided the vectors x1 t1, x2 t1, x1 t0, x2 t0, etc. xn t0 form a linearly independent set. Okay, so that gives the linear independence of this, and therefore the linear independence of phi 1, phi 2, etc. phi n, which form a solution base or a basis for the solution space. And what are the corresponding initial conditions? The initial conditions are phi 1 t0, phi 1 derivative t0, etc. or I would put the general thing is phi I t0, phi I derivative t0, etc. phi I n minus first derivative at t0 is what you call the initial data. So once you choose the n linearly independent vectors and use them as the initial data and get the corresponding solutions of the homogeneous equation, then they are linearly independent and they form a basis. When does that happen? Let us see. So you see that these vectors are linearly independent. These vectors are linearly independent if and only if the determinant of the matrix of them is not equal to 0 for any t. Okay, so what you have is this. So you designate this by it's a function of t, and this you designate as determinant of this matrix. That's the definition. So you want this to be not equal to 0. The determinant of this is not equal to 0 is the condition. Now you see that these vectors are linearly independent provided x1, x2, etc. xn are linearly independent. Now you see that if these vectors are linearly independent, only trivial linear combination can be 0. Similarly, only trivial linear combination can be over. In fact, this is what you can do. See, xt identically equal to 0 if and only if xt not equal to 0. Okay, xt is the solution of xt is dx by dt x. Now this relation we have already. Okay, if you take the 0 initial condition, then the corresponding solution is identically 0 solution, and consequently for the homogeneous equation, nth order equation, it is the first component is identically equal to 0, etc. So those connections are there that you can easily read out. So the art of getting a basis for the solution space is set up n linearly independent vectors in Rn, use them as initial data, get the corresponding solution, and you know that the existence and uniqueness theory tells that for each such choice there is a unique solution defined on the entire interval t1 to t2, because with our assumption on PIs, see, you have all the necessary ingredients to prove the existence and uniqueness theorem. Then it is defined on the whole interval t1 to t2. Now this is the information that we already have. Okay. Now that is now, you know, related to the Wronskian. Okay. So we can say that phi 1, phi 2, phi n are linearly independent. I mean, see, this is something which you can immediately prove. Phi n, phi I, of equal to 0 is linearly independent if and only if does not vanish for C2, and that is equivalent to W of phi 1, phi 2, etc., phi n evaluated at t naught is not equal to 0, for some t naught. You know that if it is, see, this is the important part. These are solutions, not arbitrary functions. Once they are solutions of this equation, they are not arbitrary. Okay? What we have is that these functions are linearly independent if and only if the Wronskian is not equal to 0 for every t belonging to t1, t2, which is equivalent to W phi 1, phi 2, etc., phi n at t naught is not equal to 0 for some t naught belonging to t1, t2. How does this come? Suppose, see, this is easy. If W phi 1, phi 2, phi n is t is not equal to 0 for every t, then it is in particular true at some t naught. Conversely, suppose you know this, then what do you infer? You infer that these vectors that you have, which are initial conditions, okay, these vectors evaluated, that is x1, x2, etc., xn evaluated at t naught form a set of n linearly independent vectors. Now this is the meaning of that, okay, because they come as a column vectors of this particular matrix, and the determinant of that not equal to 0 means the rank of this matrix is equal to n. Therefore this is what you get. So W phi 1, phi 2, etc., phi n t naught is not equal to 0 means these vectors are linearly independent. And what is the consequence? The consequence is that capital X1, capital X2, etc., capital Xn are linearly independent, and consequently phi 1, phi 2, etc., phi n are linearly independent. So this is something that emerges immediately from this. Okay. Therefore, now what we are after is how to use this Wronskian determinant. Okay. So let us ask the following question. Suppose you drop this. Okay. That means phi 1, phi 2, phi n are arbitrary functions. Okay. And the Wronskian is, identically equal. See, the problem that you have is that two arbitrary functions may be linear independent, but still their Wronskian may vanish. I will give an example. We make this observation. Okay, so let us look at this problem. What I want to say is this: the moment you drop this condition that they are solutions of the equation, then you will have to, be cautious about using or reading the consequence of the Wronskian equal to 0, identically equal to 0, or Wronskian identically or not equal to 0, etc. Let us look at a particular example. Consider the example. Ft equal to, defined as zero for -1 less than or equal to t less than or equal to 0, and equal to t square (0 less than or equal to), that's enough. And you define gt as t square over -1 and 0 for consider these two functions. What do the graphs look like? So on the interval -1 to 1, and you see that one function is this. The first function that you have is this. Is here. Okay. Now the second function that you have is, so this is your f. This is a graph of f. The graph of g is this. This is your G. Are they linearly independent or dependent? We can easily see that one is not a scalar multiple of the other. Okay, so clearly F and G are because one is not a scalar multiple of the other. Okay, so they are linearly independent. But what about the Wronskian? Let's compute the Wronskian. What is this? This is equal to F compute this on different spaces. Now you see that on from -1 to 0, F is identically equal to 0, therefore this column becomes 0. Whereas whatever be the value of this, irrespective of this, okay, you see that the determinant is equal to 0. Further, on the interval 0 to 1, you see that G is identically equal to 0, therefore this column becomes 0, and this column, whatever be the value, you see that its determinant is equal to 0. So nevertheless, okay, so even for linearly independent functions, you can have WFG identically equal to 0. But what is happening here? See, they are not solutions of any any differential equation. That's the problem. Okay, these functions are not solutions of any homogeneous equation. Whereas if you were to assume, I mean they cannot be. If these were solutions of the homogeneous problem, then WFG identically equal to 0 would have definitely implied that F and G are linearly dependent. So they cannot be solutions of a homogeneous equation. Okay, so let us see the limitation of, not the limitation, the power of these functions being solutions of the homogeneous equation. Since they are solutions of the homogeneous equation, I underline this, you will see that W, the Wronskian, either it is equal to 0 everywhere or not equal to 0. Okay, if it is 0 at some point, then it is identically equal to 0. This is the important point. Therefore, you might ask the following question: is it possible to use the behavior of the Wronskian to study this, the linear independence and linear dependence of functions, not necessarily solutions of the equation? So the question is it possible to not necessarily solutions of any homogeneous linear equation. Now this is the question that we take up. Okay. So one thing that you observe is this. Immediately you can prove this. If the functions phi 1, phi 2, etc., phi n are linearly dependent, then the Wronskian is identically zero. So that's the first observation. Okay. So we make the following observation. See, so what do we infer from this example? That even if the functions are not linearly dependent, the Wronskian may vanish. Okay? But what we are going to assert now is that if functions phi n not necessarily solutions of order homogeneous equation with each phi I Cn over T1 T2 are linearly dependent implies W of so what does it say? When these functions are linearly dependent, then necessarily WFG is identically equal to 0, or W of phi 1, phi 2, etc., that is the Wronskian of phi 1, phi 2, phi n is identically equal to 0. So one way we can conclude, okay, You can conclude both ways if they are also solutions of this. Okay. So if phi1, phi2, phi n are linearly dependent, then W phi1, phi2, etc. phi n is identically equal to 0. But if phi1, phi2, phi n were solutions of the homogeneous linear equation, then W phi1, phi2, phi n identically equal to 0 would have definitely implied phi1, phi2, phi n are linearly dependent. In other words, what you can say is that in those circumstances, phi1, phi2, phi n would have had the property that W phi1, phi2, phi n does not vanish anywhere on the interval. Okay, but in the absence of the condition that they are solutions of the homogeneous equation, if they are linearly dependent, then the Wronskian vanishes. That is quite easy to prove because what you are looking at is this. Okay, we are assuming is the functions are linearly dependent. Not all of them. Zero. That is, some of them maybe are different from 0, such that now you differentiate it. Differentiating it n minus 1 times is equal to 0 for some t. I mean, at least you can say that for some t because these are vectors. You can find out C1, C2, Cn. There exists C1, C2, Cn, not all of them 0, such that this is equal to 0. This is identically equal to 0. What does this mean? This means if you take it at a point t naught, then this means W phi 1 at t naught equal to 0 for t naught belonging to t2. But you know t naught can be arbitrary because this relation is valid for every t. Therefore, it follows that E is identically equal to 0. So that is quite easy to prove. Okay, right? So you see that the fact that the functions are also solutions of the homogeneous equation strengthens, and you see that this Wronskian would completely tell you what exactly is the nature of these functions. They are linearly independent or they are linearly dependent. Okay, so that's the situation. So we can use this Wronskian quite powerfully once these functions are solutions of the equation. Otherwise, how far you can go? Only one inference that you can make. What is the other inference that you can make? What is the consequence of this? The consequence of this is, suppose this is not equal to 0. Okay, what is the negation of this? This is not equal to 0 for some t naught. Then Certainly these functions are linearly independent. Okay, so that is the way in which you can possibly use it. Okay, so the negation of this will give you the linear independence of phi 1, phi 2, etc., phi at some point. So that's the use of that equation, that particular part. Now we want to go further. Suppose functions, which I mean it is differentiable as many times as you want it. Okay, I am not saying, you can write instead, you can write Cn functions. Okay, right? Suppose for sufficiently smooth functions, phi n is identically equal to 0. Obviously, you have seen that you cannot infer that these functions are linearly dependent. But can you put some extra condition on this so that you can come to the conclusion? Okay. So the extra condition that we put is this. This is for t1 less than t. Okay. Suppose we put the extra condition. What is the condition? The condition that we impose is the following. Some n minus 1 of the phi i's Now let us write without loss of generality for phi n minus 1. We assume that the Wronskian, the corresponding Wronskian, is not equal to 0. The corresponding Wronskian is not equal to 0. So that's, let me write down. This is an n by n minus 1 by n minus 1 determinant, that is phi 1, phi 2, etc. n minus 1 is not equal to 0 t for so there exists some n minus 1 of them for which the Wronskian is not equal to 0. Okay. Then what you can infer is that phi 1, phi 2 linearly dependent. So you are asking the question in the reverse direction. Okay. We have seen that if the functions are linearly dependent, then the Wronskian is identically equal to 0. And we have seen an example where the functions are linearly independent, but still the Wronskian is equal to 0. Now we are going to strengthen this result. So suppose we assume that the Wronskian of phi 1, phi 2, phi n is identically equal to 0. You cannot say alone, with that condition alone, phi 1, phi 2, phi n are linearly dependent. So what more is possibly to be assumed so that you can get that inference? Okay. So what the further assumption that you need is some n minus 1 of the phi i's have their Wronskian not equal to 0 for every t. If that is also true, then this is true. Okay, let us go back to our example. So recall the our example. Now you consider the interval. Okay, consider the interval minus 1, 0, that is t1, t2. On this, you know that f1 and f2 are f and g are why? Because one of them is identically 0 on that interval. Okay, because one of them so what do you have? You have this one. This is the determinant, and you know that this is identically equal to 0. So on this portion we know that they are linearly dependent, and in that case what you have, see, you look at this part, you see that what is our f? F we defined as 0 on the interval 0 to 1. So you see that our g is not equal to 0, because I think the assumption that we made was 0. Okay. Now you see that g is not equal to 0. What is the Wronskian? The Wronskian is the determinant of the single function evaluated at that. So at every point on this interval it is not equal to 0. Therefore, the theorem is applicable to our particular equation. Okay. Similarly, on the other part of the interval. Okay. So this is now with an additional condition, you can infer that the corresponding functions phi 1, phi 2, etc., phi n are linearly dependent. Now let us compute this. Let us prove this part. The first part I have already proved. Now this is a technique which is very powerful. So you take this one. X is an arbitrary function. What does this say? This says you have determinant of you have phi n minus 1, phi n minus 1 first derivative, then the last one is x this is what we are assuming. You expand this determinant about this column. What will you get? You will end up with a n minus first order differential equation. Okay. So this is homogeneous differential equation of order n minus 1. So it is something like, you expand along this last column, you will get something like this. W that is the Wronskian of phi 1, phi 2, etc., phi n minus 1. That is this sorry, this determinant up to this, okay, times etc. This turns and we are assuming that this is not equal to 0. Therefore, you can divide by that. If you divide by that, you see you get a is not equal to 0 for any t. You can divide this and by and get a differential equation which is normalized. That means by dividing by this, we have got the leading coefficient equal to 1. So let me call that equation, that n minus first order equation, let me call that some m mx equal to 0. Where m is the corresponding equation that we have obtained. Now we observe that order of minus 1. Further, you also observe that each why is it so? Suppose you write phi I here, then you see that the ith column here and the last column here are identical. Therefore, the determinant is equal to 0 for every t. Okay. Therefore, you see that is m okay. What do you infer about this? So phi I, phi 1, phi n minus 1 are the equation mx equal to 0. And having the property that is not equal to 0. What does this mean? This implies Oh, okay, 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 okay. I will also prove this. Let me. Further, m phi n is also equal to 0. Why m phi n is 0? Okay. You will see that if I replace this by phi n, then what do I get? I get, so m phi n phi n, which is identically equal to 0. That is our assumption. So it implies phi 1 phi n are n solutions of the n minus first order linear equation, linear homogeneous equation equal to 0. Now from that it is immediately clear that, see, these are n solutions of an n minus first order linear equation, and therefore that should be linearly dependent. Essentially the technique is that you take the Wronskian of phi 1, phi 2, phi n minus 1 x and identify this as a linear homogeneous differential equation whose solutions are all the phi i's from 1 to n minus 1 and also phi n. Okay, so you have an n minus first order homogeneous linear equation and you have n solutions of this homogeneous linear equation, and you see that since the order of the equation is n minus 1, these set of functions are linearly dependent, and that completes the proof of that. Okay, right. So what is the time? Let me see. Yeah, I think I will stop here and come back at 12 o'clock. Thank you very much. I am not able to connect, unfortunately.